Year 12, this is our fourth lesson for the topic of complex numbers for the course Mathematics Extension 2. In this video, we're going to look at polynomials. So a polynomial is an equation of the form p of x is equal to an x to the power of n plus an minus 1, x to the power of n minus 1 plus dot 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 plus a1 x plus a naught. And n is called the degree, so that's the highest power. If all the coefficients are real numbers, then p of x is called a real polynomial. Now you learnt back in year 9 or year 10 that a quadratic equation can have 1, 2 or no real roots, and these are represented by x-intercepts on the graph. But here's the thing, a quadratic equation will always have exactly 2 complex roots. Which leads us to the fundamental theorem of algebra, which states that any polynomial of degree n has exactly n roots. Now the proof of the fundamental theorem of algebra is beyond the scope of the course, so we're going to look at a corollary. That means a proposition that comes after a theorem. And this corollary, which states that any polynomial of degree n is reducible to exactly n factors, is true because of the fundamental theorem of algebra, and we're going to look at the proof. We'll start by setting up a polynomial of degree n. Now, by the fundamental theorem of algebra, Pn of z has a root z1 such that Pn of z1 is equal to 0. And by the factor theorem, z minus z1 is a factor of Pn of z. And that means we can write Pn of z like this. We've got z minus z1 in brackets multiplied by a new polynomial of degree n minus 1. So let's do it again. By the fundamental theorem of algebra, we know that Pn minus 1 of z has a root z2, such that Pn minus 1 of z2 is equal to 0. And so we can write Pn of z as z minus z1 in brackets, z minus z2 in brackets, multiplied by a new polynomial, Pn minus 2 of z. And you can see where this is going. We continue the process n times, and we will get Pn of z is equal to some coefficient, an, multiplied by all of those factors together, thus showing that any polynomial is reducible to exactly n factors. A second theorem for this lesson, it's called the conjugate root theorem, and it states that complex zeros of real polynomials occur in conjugate pairs. Just before we look at the proof, we need to know some important results about conjugates. Firstly, the conjugate of a sum or a difference is equal to the sum or difference of the conjugates. In other words, if you have this plus or minus isn't going to affect that conjugate. We can split it up like this. Also, the conjugate of a product or quotient is equal to the product or quotient of the conjugate. So it also works for multiplication and division. We also have the conjugate of a power is equal to the power of the conjugate. So I'm going to split it up like this. And finally, the conjugate of a real number is the real number itself. So now let's look at the proof. Consider the polynomial p of x where all the coefficients are real. Let z be a root of the equation p of x is equal to 0. Therefore, p of z must be equal to 0. I'm going to take conjugates of both sides, like this. And remember that the conjugate of a real number is the real number, so that's just 0. And we're going to split this up using that first relationship that I showed you. Now we've got that multiplication here, so I can split this up into two conjugates, but this is a real number, so I don't need the conjugate over the top of it. And then finally we've got that power relationship, so it equals this. And so we can say that the conjugate of z is a root of this equation. And so we've proved it. Let's look at a couple of examples. Example 1. Find a quadratic equation ax squared plus bx plus c is equal to 0 if the complex conjugate roots are -1 plus or minus 3i. Now you can form a quadratic equation and expand it all out, but the sum and product of the roots is much, much easier. So recall the sum of the roots is equal to -b on a, the product of the roots is equal to c on a. So there's our sum of the roots, it's -2, and there's the product of the roots, it's 10. So we've got -2 is equal to -b on a, and we've got 10 is equal to c on a. And so if we let a equal to 1, then b is going to be equal to 2, and c is equal to 10, and so our quadratic equation is x squared plus 2x plus 10 is equal to 0. Here's example 2. Part A. Show that z take away in brackets 1 plus I is a factor of z cubed minus 4z squared plus 6z minus 4. So all we're going to do is take 1 plus I and substitute it in here, and hopefully we will get 0. So it equals 1 plus I all cubed, take away 4 times 1 plus I squared plus 6 times 1 plus I, take away 4, expanding it out, and then collecting like terms, we end up with 0. Therefore, by the factor theorem, z take away in brackets 1 plus I is a factor. Part B, find the other two factors. So we know that z take away 1 plus I in brackets is a factor, and so z minus 1 minus I in brackets must also be a factor. So let's multiply those two together. Now I'm going to expand out in these brackets here and group them in a different way. I've got z minus 1 at the beginning of both of these brackets, and then I've got minus I plus I, so I can do the difference of two squares like this. It's just quicker. Expanding out and tidying up, I end up with z squared minus 2z plus 2. Now, it might be tempting to do polynomial division, but it is overkill. Remember, division and multiplication are opposites, so sometimes you can get there faster through multiplication. Have a look at this. Just multiply these last two terms. We can see easily that a has to be equal to 2, but you can check it if you want to. So our factors are z take away in brackets 1 plus or minus I and z minus 2. And example 3, factorise z cubed plus 3z squared plus 2z plus 6 over the set of real numbers. Again, tempting to use polynomial division, but with a cubic, always consider that you might be able to factorise the first two terms and the second two terms and get a common factor. And in this case, you actually can. See the common factor of z plus 3? So the factorisation is z squared plus 2 multiplied by z plus 3. Now over the field of complex numbers, we need to further factorise this here. Now remember how you do this? We're going to change that plus 2 into negative 2i squared, and then use the difference of 2 squared. So fully factorised, we have z minus root 2i, z plus root 2i, z plus 3. Finish off this part by looking at a past exam question. Solve z squared plus 3z plus 3 minus I equals 0, giving your answer or answers in the form a plus bi, where a and b are real. Okay, nice easy question. We're going to apply the quadratic formula. So z is equal to -3 plus or minus the square root of 9, take away 4 times 1 times 3 minus I all over 2. And let's tidy that up. Now, we can't go any further because we need to know the square roots of the complex number -3 plus 4i. Now I'm going to skip over how to find the square roots because we've already covered that. The square root of -3 plus 4i is plus or minus 1 plus or minus 2i. Now looking back to our equation for z from the quadratic formula, when I substitute in here, I only need to substitute in one of these because I've got a plus minus here. So I'm going to substitute in 1 plus 2i. Now we're going to work through the answer with the plus sign and then work through the answer with the minus sign, and we will get two solutions, -2 plus 2i all over 2 and -4 minus 2i all over 2. which can be further simplified to -1 plus I and -2 minus I. Okay, this is our last bit for this lesson. It's on roots of multiplicity. P of z is reducible to exactly n factors. We learned that right at the beginning of the lesson. It's the fundamental theorem of algebra. But they don't all have to be different. Recall, if we've got y is equal to x minus 1 all squared multiplied by x minus 3 all cubed, there are zeros at x is equal to 1 and 3. But the 0 at x equals 1 has multiplicity 2. It's called a double root. And the 0 at x equals 3 has multiplicity 3. It's called a triple root. So here's our theorem. If z equals c is a 0 of multiplicity r of the polynomial p of z, then z equals c, the same 0, is a 0 of multiplicity r minus 1 of the derivative of p of z. Now, the proof is outside the scope of this course, but this is a really useful theorem. Here's an example. Solve p of z is equal to 0 given the polynomial has a root of multiplicity 2. So we're going to start by differentiating. Now we'll let the root be z is equal to a, and that means when we substitute it in, we will get 0. So we need to solve this cubic. Now, I can't factorize the first two and the last two and do that quick method, so we're going to need to find a root of this polynomial and then use polynomial division. So through trial and error, z equals 3 is a root of the equation p dashed of a. And that means that we can write p of z like this. Here's our root of multiplicity 2, and then we're going to multiply it by some other polynomial, q of z. Okay, here comes our polynomial division. So z minus 3 all squared is z squared minus 6z plus 9, and we are going to divide that into p of z. So z squared into z to the power of 4 goes z squared, multiply z squared by this, and subtract. We have got minus 5z cubed, take away negative 6z cubed, 4z squared, take away 9z squared, and bring down our next term. Z squared into z cubed goes z. Multiply z by all of this underneath and subtract. And we're going to get negative 5z squared, take away negative 6z squared, and 3z take away 9z, and bring our last term down. And then that goes into that once. And so p of z is equal to z minus 3 all squared multiplied by z squared plus z plus 1. And we want to solve this equal to 0. We can see that z is equal to 3. I'm just going to use the quadratic formula to find the solutions here. So tidying that up, we end up with 3 and negative 1 plus or minus root 3i all over 2. Okay, that's it. Our next lesson is on powers and roots.